In this lesson, we're going to look at samples and populations, problem 4.2, and the idea of looking at a scattered data plot like this one where the data is kind of in dots in many places, but then being able to actually write an equation, or really the idea would be to be able to come up with a way of using this to describe a trend and then use it to make predictions. And so the data that we're given in this case is 54 sixth grade students. They measure their arm span, so from arm tip to arm tip, and then their height. And these are the numbers that show up on there. And really the question is if you know someone's height, can you then predict their arm span? Is there a relationship between this distance and this distance? And some of you may have actually tried this for yourself and measured your arm span and your height and found that there's fairly close correlation between those two distances. They're not always exactly the same, but they're fairly close. And you can see from this scattered data plot that, yes, that's something that seems to be fairly clear, that as the height increases, so does the arm span, but they're fairly equal. So the idea would be that I could actually draw a line through that data, and you can see that that line actually goes through most of the data, kind of through the middle. We call that sort of a trend line or a best fit line, the trend going through here, and it goes through data points. It goes to this point 130, where the height is 130 centimeters, and the arm span is 130 centimeters, and all the way on up to this top point here where it's 190 centimeters, and actually the point value 190, 190, and this one 130, 130. And the question is, could we write an equation for that line? Well, this is a fairly simple equation because this represents a value of x, 130, and this represents a value of y, 130, and this up here represents a value of x, 190, and a value of y, 190. And so really we could simply just say that, in this case, y, the arm span, this is y, there's a y there on our graph, and x, these are just variables that are used to represent something. X is your height. So we could really just simply say that your height is equal to your arm span. Or we could put this in algebra terms and say that your height x is equal to y, or y is equal to x. Sometimes we would say that. That's an equation. You equate one thing to another. Your height is equated to your arm span. Those two things are approximately equal. You can see it's not exact, but we can generally predict. If you know one, you know approximately the other. And so that's why we call this a trend line, or maybe a best fit line. It's not exactly through all those dots. Every person is not exactly the same. But generally speaking, arm span is equal to height. And you can see that through the scattered data on this. So we could kind of say that for each point, we could pick a point like 150 centimeters for a height would give you 150 centimeters for an arm span, or 160 centimeters. So each of these data points along here, we could use any one of them to use a description. If you're 180 centimeters tall, we would expect your arm span to be about 180 centimeters. So that's where we use these kinds of relationships and scattered data to do that. Now, the second part of this problem deals with a very similar kind of situation where if you had airplanes, and there are different kinds of airplanes, jet airplanes and propeller airplanes, and if you measured the body length of an airplane and compared it to its wingspan, and you can see there's some variation between the two. But if we were to take that data, and I'm going to kind of show you what I did for this particular problem. If we were to take that data and we were to put these into lists in our calculator, so this part here, I actually did this into 4 lists because I wanted to take jet body length and jet wingspan. So that's my list 1. and list 2 for jet, body length, and jet wingspan. So I put those into my calculator, and if this is something you want to do along with me, you might want to pause the video right now and go ahead and do that. I've already done it. So list 1 and list 2 are my jet plane body length, list 1, wingspan, and list 2. So you can see where those are in there. And then I went down and in list 3 put propeller airplane body length, and list 4 the wingspan of those propeller planes. Two kinds of planes, jet planes, propeller planes, body length, wingspan. So list 1, list 2, list 3, list 4, and that gave me 4 lists. And then I was able to go into my plots and do scatter data plot for list 1 and list 2. So the scatter data plot is this first plot on your calculator. I'll zoom in a little bit so you can see those better now. We're focusing on the graphing calculator. And so I have my scatter data plot, and I have list 1 and list 2, which are the jet plane body length and the jet plane wingspan. And I'm using this mark for those. And then I went in and in plot 2, I did lists 3 and 4 for a scatter plot. So I got my scatter plot on, put in list 3 and list 4 by going second list, or with a TI-83 just pushing second and the number on your keyboard for the list you want. And then I want to use the plus sign for this because I want to actually be able to differentiate between the jet planes and the propeller planes. And then I went ahead and graphed it. And so now this is what you see in terms of the trend of the data. The little plus signs being the propeller planes and the square ones being the jet planes. And really all that's showing you is that, you know, as the body length increases, so does the wingspan, and you have, you know, jet planes of all different sizes and your propeller planes of all different sizes. And so as the body length increases, so does the wingspan, and in a fairly regular manner. Now if you remember in the first problem we said that body length and wingspan, body length and arm span for people are about the same. And the question is, would that be about the same for airplanes as well? So I'm actually going to push this y equals button here. I'm going to put in an equation because we said that body length and wingspan were equal, and we said y equals x. There's an x button on your calculator. And for me it's next to the 7. On an 83 it's up above in this area here above the 7. And so if I said y equals x, and I actually hit graph now, it's going to put in a line there. And so that would be that if y equals x, and you see it's not perfect, it doesn't go exactly through all the points, but in general it trends upward through them. So we have this consistent upward trend. So again, we could say that even for airplanes, the body length and wingspan is about equal. You have some here that are a little below the line, some above the line. So it's not exactly an equal ratio. Maybe might be slightly less than a 1-to-1 ratio. But again, the idea is that if you have an airplane with a wingspan of about 60 meters, you would expect its body length to be about the same, 60 meters. If you had an airplane with any particular wingspan, if the body length was 100 meters, then you would expect the wingspan to be about 100. So it looks like airplanes use a similar ratio that people do. Now, the challenge comes in that when you get to the third part of this, is that if you think about birds, and we're not going to really get an equation for this, but the idea would be that if you're looking at birds and the trend with birds, their body length and wingspan are not exactly in the same ratio that people are. So you can see as their body length increases, so body length is increasing, wingspan is increasing even faster. So it's not a 1-to-1. If I look at 20 here, a body length of 20, it looks like the wingspan is 40. If I look at a body length of 40, the wingspan is 80, 85, 90. So the wingspan for birds is about twice as much, or a little over 2 times their body length. And that I'm sure has something to do with the necessity for flying and wings and the muscles it takes to do that for birds, that they need to have longer wingspan than body length to do that, to make them able to fly. So that's my best fit line through that data that fits that. And an equation for that line, I might just say that this is my y, this is my x, and so I said before it's about twice as much. So 40 is around 80, 60 would be around 120, or maybe it's a little bit less than that, but that's still approximately enough. So I would say y is equal to 2x would be an equation I could use to describe the wingspan. So this is my wingspan y, and my body length x. So if you take the body length of a bird, like if it's 60, you would expect its wings to be, at least 120 inches long, body length. So as the body length increases, the wingspan is actually twice as much as that. And so if I had a 60-inch body length, I would expect a 120-inch wingspan. And so that's how we can use equations and scattered data plots to predict or make predictions for data. Even though the data is not exact, it still gives us an idea or a trend. This is a positive correlation, a positive trend. As this increases, so does this. This one, in this case, the wingspan twice as much as the body length. And so again, we can use data to make predictions. Not exact in this case, but at least giving us an idea or a general representation of what is happening in any particular situation. And so that's how you use scatter plots or scattered data plots to make predictions and even to write equations for this, which we'll look more at in future lessons about how to write equations using lines and scattered data.